Hey, my dear students, welcome back. Again, I want to say thank you so much for your support. The topic that we are going to discuss in this video is about the solubility equilibria and the precipitation reaction. So let's dive into it. Two most common ways to express a substance solubility are molar solubility and solubility. Molar solubility, which is the number of moles of solute in 1 liter of saturated solution, expressed in mole per liter. The second one is solubility, which is the number of grams of solute in 1 liter of saturated solution in gram per liter. Note that both of these expressions refer to the concentration measured at 25 degrees Celsius. We are going to see through examples how to find the molar solubility and solubility of an ionic compound. If two soluble constants are given, how to find which is more soluble, effect of the common ion in the solubility, how to find if a reaction forms precipitate or not. But first, let's take a look at solubility product constant. Take a look, for example, at silver chloride. It dissociates in silver plus and chlorine minus. The solubility product of silver chloride is equal to the concentration of silver ion multiplied by the concentration of chlorine ion at a saturated solution. For calcium fluoride, but in this case you have to be careful, you have to raise to the power 2 the concentration of fluoride due to the coefficient here. But when is going to precipitate a solution? If the ionic product is smaller than solubility product, we are dealing with an unsaturated solution, so we are not going to have precipitation. If ionic product is equal to the solubility product, we are dealing with a saturated solution. We are at equilibrium. No precipitation yet. If the ionic product is higher compared to the solubility product, we are dealing with a supersaturated solution that is unstable, and eventually it will precipitate out until the product of the ionic concentration is equal again to the solubility product, until we reach to this point here. Let's move now to the first example that deals with molar solubility. What is the molar solubility of calcium fluoride in pure water first? First, what we are going to do, we are going to dissociate the calcium fluoride to calcium 2 plus. After that, we are going to write the solubility product. We have given the solubility product for calcium fluoride, so we need to find the molar solubility. What we are going to do, we are going to write S for calcium concentration ions and 2S for fluorine, because we have 2 fluorine, and solubility product is going to be equal S multiplied by 2S to power 2 due to this one, and it's going to be equal to what? 1.46 multiplied by 10 to minus 10. Be careful here. If you have a coefficient 2, it's going to be here at the solubility product and also raised to the power of that coefficient. So solubility, so we are going to have 4s cubed equal to, so the solubility in pure water is going to be, the root is going to have third power, so divided by 4. In order to do this kind of calculation, you need to use a scientific calculator, like this one, for example. This calculation gives us 3.3 times 10 to power 4 mole per liter. What if we want to find the gram per liter solubility? It's simple. Just multiply with the molar mass, the concentration in mole per liter. Molar mass for calcium fluoride, you are going to find it from the periodic table, and is 78.07 gram per 1 mole. So mole with mole simplify and remains only gram per liter. So this is going to be equal to 0.026 gram per liter. This is another way that we can express the solubility. So let's move now to the point B. Sodium fluoride itself dissociate completely, is a soluble salt in sodium plus, fluoride minus. But since the sodium is 0.2 molar, also this one by the stoichiometry is 0.2 molar, and also this one is 0.2 molar. So when we are going to calculate the solubility product in this case, we are going to consider also the concentration of the fluorine that comes from this soluble salt. What is going to happen theoretically? According to the Le Chatelier principle, you are adding a common ion. So you are increasing the concentration of fluorine ions. So the system is going to shift to the left to minimize the disturbance. So we are going to consider in our calculation this concentration that we have here. So the solubility product constant is going to be equal to S for calcium multiplied by what? 2S for the fluorine here, plus 0.2 molar that comes from the fluorine that comes from the soluble salt. So we are going to do a simplification. This is going to be equal to 1.46 multiplied by 10 to minus 10. So we are going to do a simplification here by considering around 0.2 because this value is too small compared to 0.2 molar that we add from the soluble salt. So it's going to be S multiplied by 0.2 square equal to 1.46 times 10 to minus 10. So S is going to be 3.65 times 10 to power minus 9. As you can see here, the solubility in the presence of the common ion, like in this case of the fluorine, decreased dramatically the solubility of calcium fluoride compared to that one that we have in the pure water that we calculated before. In general, common ion decrease the solubility of an ionic compound. Let's move now to a second example. Here we are going to compare who is more soluble. If we have two solubility products, we have to be careful. We have to find the solubility of each ionic compound to make sure who is more soluble, because in this case looks like that the iron phosphate is more soluble than the calcium phosphate with a difference of 10. But let's do the calculation and see that is not true. That's why I recommend to do always the calculation if you have this type of exercise in your exam. So we are going to dissociate both salts, and to find the solubility of each of them. So what we are going to have? Solubility product for the first one is going to be 3S to power 3 multiplied by 2S to power 2. And for the iron phosphate, solubility product, S multiplied by S. So if we do the calculation for the first one, we are going to have 27S cube multiplied by 4S square equal to what? 1.3 times 10 to power minus 32. And for the second one, square S is going to be equal to 1 to power minus 22. So S, solubility for iron phosphate, is going to be, now it's 2 here, it's not written normally, and is 10 to power minus 22. You can do this directly, so it's going to be 10 to power minus 11. Okay? This is the solubility for the iron phosphate. Let's check solubility for the calcium phosphate. So this is going to be 108 S to power 5 multiplied by equal to. Again, here for doing this calculation you need a scientific calculator. Solubility for the calcium phosphate is 1.64 times 10 to minus 7, which is higher compared to 10 to minus 11, that is the solubility of iron phosphate. That's why I told you that you always have to calculate. Let's move now to see the effect of the pH in the solubility. Calculate the molar solubility of manganese hydroxide in pure water and in a solution buffered at pH 10. In pure water, as you saw in the previous example, is simple. So we are going to dissociate manganese hydroxide and the solubility product is 5 times 10 to minus 14. So solubility product is going to be equal to concentration of manganese multiplied by concentration of OH minus to power 2. If you want to find the impure water, I'm leaving that to you, and write it in the comment down below. The answer should be 2.3 times 10 to minus 5 molar. Impure water solubility. But what about in a solution buffered at pH equal to 10? At this point, you need to find the concentration of OH minus in the solution, and after that to find the solubility. So you should know that pH plus POH is equal to 14, ionic product of water. So from here you can find POH, that is 14 minus pH. So 14 minus 10 is equal to 4. And you should know that POH is equal minus logarithm of OH minus concentration. So in this case, concentration of OH minus is going to be what? This is the exponent of the power, so it's going to be 10 to minus 4. So now that we found the concentration of OH minus, we need to find the concentration of manganese ions. So solubility product is going to be S multiplied by what? 10 to power minus 4, that is the concentration of OH from this buffered solution, to power 2, equal to the solubility product constant. So this is going to be S equal to 5 multiplied by 10 to minus 14 divided by 10 to power minus 8. It's going to be equal to 5 multiplied by 10 to power minus 6 molar, which is smaller compared to 10 to power minus 5 in the pure water. So as you can see, in this case, the effect of the pH decrease the solubility of manganese hydroxide. Let's move now to the point C. Does a precipitate form in point B if we add to the solution 0.2 molar of manganese chloride? In this case, we are going to use the ionic product, or Q. We are going to calculate Q at the beginning. We are going to calculate Q and compare it with the solubility product constant. So Q is going to be equal, again, concentration of manganese 2 plus multiplied by concentration of OH minus to power 2. This one we found from the buffered solution in point B, that was 10 to minus 4 molar. This one here is 0.2 molar because manganese chloride is a soluble salt and dissociating manganese 2 plus chloride minus, 2 chloride minus. This is 0.2 molar from the stoichiometry. This one is again 0.2 molar. This one is 0.4 molar, but it's not in our interest. In our interest is the concentration of manganese 2 plus ions. So we are going to calculate Q. Q is going to be what? S plus 0.2 molar multiplied by 10 to power minus 4, that is the concentration of OH minus, to power 2. So what we are going to have, this is going to be around 0.2 because S is too small, and Q is going to be equal to what? 2 to power 10 to minus 7, which is higher compared to 10 to power minus 14 that was the KSP, or solubility product, for manganese hydroxide that we had at the beginning. So since Q is higher than KSP, we are going to have precipitation. Okay, let's move now to another example to predict if an ionic compound is going to precipitate or no. Predict whether a precipitate will form if you mixed 75 ml of sodium hydroxide solution with pH 11.42 with 125 ml of 0.18 molar manganese chloride solution. Solubility product for manganese hydroxide is 2.06 times 10 to power minus 13. First, let's write the reaction, that is sodium hydroxide plus manganese chloride is going to give us manganese hydroxide plus sodium chloride. So here we are going to have a 2 and here a 2, and the equation is balanced. So we need to deal with this one, manganese hydroxide. If the ionic, so in order to find if it precipitate, we are going to find the ionic product first and compare it to the solubility product constant. So what we have a container that we add 75 milliliter of sodium hydroxide and we add 125 milliliter of manganese chloride. So the total volume of this container is going to be 200 milliliter. So keep in mind, even without starting the calculation, that we have a dilution of our solution. So what we are going to find? We are going to find, first let's write the solubility product for manganese hydroxide, that is concentration of manganese 2 plus multiplied by the OH minus to power 2, because manganese hydroxide dissociate to manganese 2 plus 2OH minus. So we need to find the concentration of manganese and the concentration of OH, and after that we are going to calculate the Q, and after that we are going to compare it with the solubility product. So what we are going to do? So as we saw from the previous example, POH is going to be 14 minus pH. So it's going to be 14 minus 11.42. So it's going to be equal to 2.58. This is the POH. So the concentration of OH minus is going to be what? 10 to power minus 2.58. And if you calculate by a scientific calculator here, it's going to be 2.6 times 10 to power minus 3 molar. So we found the concentration of OH minus that is contained at this pH 11.42 at 75 milliliter. But we have dilution of our solution. So we are going to calculate the new concentration of OH by considering the 200 milliliter. That is that relation CM1 molar multiplied by the volume 1 equal to molar concentration 2 multiplied by the volume 2. So the concentration of OH in the container is going to be 2.6 multiplied by 10 to minus 3 molar multiplied by what? 75 milliliter divided by what? 200 milliliter, by using this formula. This is going to be equal to 9.75 multiplied by 10 to power minus 4 molar. Be careful, you have to consider the dilution of the solution. So for the other one, we have a soluble salt that is 0.18 molar, 0.018 molar. So manganese chloride completely dissociate to manganese 2 plus 2 chloride minus. This is 0.018 molar. This is going to be by the stoichiometry 0.018 molar in the completely soluble salts, and this is going to be double 0.036 molar, but we are not interested on this one. We are interested on manganese. So again, concentration of manganese after the dilution is going to be what? 0.018 molar multiplied by what? 125 milliliter divided by 200 milliliter. Again, the same formula, CM1 multiplied by V1 equal to CM2 multiplied by V2. So this is going to be equal to 0.011 molar. Here, now we have the right to calculate the Q. That is equal to S for manganese multiplied by 2S squared, because we have manganese hydroxide that dissociate into manganese 2 plus plus 2OH minus. That's why we have the right to write this one S. You can write also X instead of S, but S it's like solubility. So Q is going to be equal to 0.011, that is the concentration of manganese, S, this one here, multiplied by what? The concentration of OH, that is 9.75, multiplied by 10 to power minus 4 to square. Okay? This is the concentration. Something to consider here, you're not going to multiply by 2 this expression here. You're going to leave as it is, because this is the concentration of OH. This 2 is included inside to this one. So do not multiply there. So Q is going to be equal to 1.04 multiplied by 10 to power minus 8, which is bigger than 2.06 multiplied by 10 to power minus 13. So we are going to have precipitation. Alright, so that's it for this video. Hope it was a little bit helpful to understand the solubility equilibria, and see you in the next video. Peace.